before starting your session, it is my pleasure to introduce Mr. Dhrumil Gogri and Mr. Ekaansh Arora, two dynamic young innovators and co-founders of Hydrogen Network India, who are jointly leading today's session on role of academia and industry in hydrogen R&D. Together, they bring a remarkable blend of industrial, academic, design, and engineering expertise and are actively shaping India's emerging hydrogen ecosystem. Mr. Dhrumil Gargi is a manufacturing process and design engineer and a hydrogen technologist with deep industry experience in fuel cell, mechanical design, hydrogen system integration, and advanced manufacturing. His background includes significant work at Loop Energy Inc., Canada, where he contributed to fuel cell stack design, GD and T based precision engineering, PFD, PD, P&ID development, and lean manufacturing optimization. He currently serves as a co-founder and director of Hydrogen Network India, where he leads efforts in hydrogen skill development, fuel cell training modules, design of ultralight hydrogen fuel cell power systems, and hydrogen-based microgrid solutions. His contributions reflect strong industry academia collaboration and a commitment to enabling India's transition towards hydrogen powered mobility and decentralized clean energy. And Mr. Ekaansh Arora is a chemical process engineer with distinguished academic credentials from the University of British Columbia, where he graduated with distinction and received multiple honors, including the Sherman Chen Scholarship. His research and engineering experience spans fuel cell durability testing, hydrogen safety process optimization, data automation, and techno-economic assessments. He has worked exclusively at AVL Fuel Cell Canada, managing fuel cell test stations, optimizing PEMFC performance, developing automated analysis tools, and performing advanced material diagnostics, all contributing to improved reliability and safety of hydrogen systems. In academia, he has led notable hydrogen projects such as pilot scale methane pyrolysis plant design, techno-economic modeling for hydrogen production, CO2 capture system design, and thermal integration and LCA studies, with several projects featured at UBC for innovation. Together, Mr. Gorgi and Mr. Arora bring strong industry experience across hydrogen mobility, electrolyzers, and fuel cells, deep understanding of R&D, safety, TEA, and system design, proven ability to translate academic research into practical industrial solutions, commitment to advancing hydrogen training, innovation, and entrepreneurship in India. Their combined expertise makes them highly suited to speak on crucial roles that academia, industry, and startups play in accelerating hydrogen research, technology development, and deployment. Please join me in warmly welcoming Mr. Dhrumil Gargi and Mr. Ekaansh Arora to deliver today's session. I think participants will be most benefited as they are from Hydrogen Network India and industry. So please also interact with with them after the talk. Yeah, you may proceed with the presentation, Mr. Gorgi.
Can you see my screen?
Yeah,
Yes, sir.
Okay, thank you so much, Dr. Bhargavi, for the warm introduction, and a very good evening to all the esteemed faculty members, researchers, and students joining us today. We're truly honored to be here, and we sincerely appreciate NIT Raipur for hosting this session and giving us the opportunity to speak with such a distinguished academic community. Uh, we're excited to discuss the role of academia and industry in accelerating hydrogen R&D. And we hope this session sparks new ideas, collaborations, and pathways for innovation. So, our topic for today is the role of academia industry in hydrogen R&D in India, driving innovation, collaboration, and commercialization for a green hydrogen future. So, this is an extremely important topic and timely theme because India's hydrogen journey cannot move forward without strong collaboration across universities, research institutions, industrial partners, and innovators. And in this session, we will explore how academic research, industry driven development, and entrepreneurial initiatives are collectively accelerating hydrogen technologies in India. We will discuss how policies, R&D programs, and national missions have opened new pathways for innovation and how institutes like NIT Raipur can position themselves at the forefront of this transformation. So, our goal today is to help you understand where the opportunities lie in research, in funding, in industrial partnership, in skill development, and in emerging hydrogen technologies that are ready for academic industrial collaboration. So, with that, let us begin our deep dive into how academia and industry together can drive India's green hydrogen future. So, I just quickly like to walk you through the key objectives of today's session. Our focus is to give you a clear understanding of how green hydrogen R&D landscape is evolving in India. So first we look at major R&D policies, schemes, and national programs under the National Green Hydrogen Mission and related government bodies. Then we'll map out the current research ecosystem, the roles of academia, national labs, startups, and industry, and how they contribute to innovation in green hydrogen technologies. Then we'll explore emerging research opportunities, including high impact areas such as advanced materials, electrolyzer innovation, hydrogen storage, safety engineering, and waste to hydrogen pathways. And from there, we'll move into one of the most important aspects for any researcher, pathways to fundraise. And then we'll look at government grants, international collaborations, corporate R&D partnerships, and industry-driven funding models for hydrogen research. And finally, we'll discuss strategic opportunities for NIT Raipur, where the institute can play a leading role, the kind of projects that can be initiated, and how faculty and students can directly engage with India's hydrogen future. Uh, we already did the introduction, so I'll just skip this for now. So, yeah, now let's take a look at government's major schemes and programs that directly support green hydrogen R&D in India. So this is important because funding, mission alignment, and policy direction determine how quickly innovation can move from academia to industry. So we have the National Green Hydrogen Mission, where under the National Green Hydrogen Mission, the government of India has allocated a total outlay of 19,744 crores for the period 2023 to 2030. Within this, there is a dedicated R&D budget of 400 crores specifically targeted at technology development, innovation, and ingenious capability building. Additionally, for financial year 2024-2025, the government has assigned roughly 600 crores in annual kickstart funding to accelerate early stage hydrogen research and pilot development. And then we have the key R&D programs and instruments. So the first major mechanism in this R&D scheme under NGHM is where MNRE issued a call for proposals on 15th March 2024, followed by a second call on 14th July with a deadline of 15 September 2025. These calls focus on accelerating indigenous technologies, lowering costs, and enabling India's led breakthroughs. And then the second instrument is the Strategic Hydrogen Innovation Partnership, or SHIP. This is a public-private platform for mission-oriented research. SHIP is designed to support high-impact collaborative R&D, including pilot demonstrations and commercialization-ready technologies. And then we have the site incentive program, which many of you may already be familiar with. Although site is primarily focused on electrolyzer manufacturing and scale up, it complements the R&D ecosystem by creating a pathway for technologies developed in the lab to reach commercial deployment. And finally, we have the priority R&D areas as defined by the government. So the government clearly defined uh, identified priority research areas. Those include advanced electrolyzer technologies such as AEM, PEM, SOEC, as well as catalytic materials, membranes, stack components, and methods to improve system efficiency. Hydrogen storage is another major focus, covering metal hydride, LOHCs, solid state storage, and high pressure compressed systems. There is a strong emphasis on safety, transport standards, and certification frameworks, which we'll get into later in this presentation. And then we have power to X technologies, such as hydrogen to ammonia, methanol, and other e-fuels, are also key areas, especially for industrial scale pilots. And finally, electrolyzer integration has become critical, and combining renewables with electrolyzers and developing advanced control strategies and enabling grid stability. And together, these programs create one of the strongest R&D support ecosystem that India has ever built for an emerging clean energy technology. And this is the right time for academic institutions like NIT Raipur to tap into these schemes and play a leading role in hydrogen innovation. So, India is standing at a remarkable crossroads in its energy journey as one of the fastest growing economies in the world. Our energy demand is expected to more than double by 2040. And to meet this demand without compromising our climate commitments, we need solutions that are both sustainable and scalable. And this is where hydrogen becomes a game changer. So, hydrogen is often called the fuel of the future, but for India, it's quickly becoming the fuel of the present. And with the National Green Hydrogen Mission, the government of India has committed an investment of 19,744 crores, as mentioned before, targeting 5 million tons per annum of green hydrogen production by 2030. That's not just a policy goal, it's a national movement towards cleaner mobility, decarbonized industry, and energy independence. Hydrogen has the unique ability to store renewable energy, replace fossil fuels in industries like steel and refining, and power heavy vehicles and ships that are hard to electrify. However, achieving this vision isn't just about scaling up production, it's about innovation. And hydrogen technologies, whether it's electrolyzers, fuel cells, storage system, or safety mechanisms, are still evolving. We need continuous research and development to make them more efficient, durable, and affordable. And that's where collaboration becomes essential. Academia brings deep scientific expertise such as new catalysts, membranes, different simulation models, and then the industry brings the ability to manufacture, scale, and commercialize those technologies. And the government provides framework, funding, and long term policy support. And with these three, when these three come together, uh, they form what we call the triple helix of innovation. And it's the helix that truly powers hydrogen revolution in India. Now let's take a closer look at the major hydrogen schemes that the government of India has launched to accelerate manufacturing, R&D, innovation, and commercialization in the green hydrogen sector. So the first and the largest scheme under the National Green Hydrogen Mission is the SITE program. With an outlay of 17,490 crore, SITE is designed to boost domestic manufacturing of electrolyzers and scale up green hydrogen production. The goal is to build India's core manufacturing capacity so that our hydrogen ecosystem is competitive globally. Next, we have the pilot project scheme. So, alongside manufacturing, the government has allocated 1,466 crores specifically for pilot projects. These focus on real world demonstration in steel, shipping, mobility, and emerging applications. These pilots are extremely important because they validate technologies, create market confidence, and accelerate commercial adoption. Next, for research and innovation, the government has earmarked 400 crores under the dedicated R&D scheme. This supports collaborative consortia involving IITs, CSIR labs, national institutions, and industry partners. And so far, 23 projects have been supported. And the second round of calls was issued in July 2025, including opportunities for international collaboration, such as joint proposals with the European Union. Next is the startup support call, recognizing the importance of innovation and entrepreneurship. This mission also includes 100 crore rupees for startup support call, and this provides up to 5 crore per startup for pilots, prototypes, and breakthrough technologies. This is a major opportunity for young innovators entering the hydrogen space. Another significant mechanism is SHIP, the Strategic Hydrogen Innovation Partnership. SHIP acts as national level R&D consortium, bringing together BARC, ISRO, CSIR, IITs, IISCs, industry partners, and startups. The idea is to drive mission-oriented research where academia and industry work together from day one to deliver deployable hydrogen technologies. Next, we have lastly the Hydrogen Research Initiative under DST continues to support advanced research in hydrogen production, storage, distribution, safety, and novel applications through its hydrogen and fuel cell program. This scheme plays a crucial role in building long-term scientific capability and supporting fundamental research. And since we're talking about so much investment, uh, to understand the scale of India's ambition, let's break down what it actually takes to produce 5 million tons of green hydrogen per year, which is the goal by 2030. So, this target sits at the core of the National Green Hydrogen Mission, and infrastructure needed is enormous. So, this mission aims for 5 million tons per annum of green hydrogen, and the associated electricity requirement is on the scale of what this entire countries consume. So, producing 5 million tons per annum of hydrogen requires about 250 terawatt hour of electricity per year, which converts into a continuous power demand of 28.5 gigawatt operating 24/7. And if we rely on solar energy to get all the electricity we need to power the electrolyzers we will be putting, we would need 114 gigawatt of dedicated solar capacity, roughly 254 million solar panels, 450 watt each, with a surface area of about 558 kilometers square just in panel surface area. But if we include the spacing, shading inverters, and all the infrastructure that goes with it, it comes up to be about 1100 to 1400 kilometers square, which is 340,000 acres, which is the size of Delhi NCR or two times the size of Mumbai. And then if we talk about the electrolyzer requirements, we need to continuously operate at 28.5 gigawatt and 2,854 plants of 10 megawatt each for 24/7 renewable supply. However, if we operate only on solar, which runs at 25% utilization, we would need 11,416 plants of 10 megawatt each. And to put this into perspective, the image on the right is Gale's new 10 megawatt green hydrogen plant, one of the largest operational units in India right now. And using this as a reference point, achieving 5 megaton per annum would require about 2,854 Gale-sized plants if they run continuously using renewable energy, and around 11,416 Gale-sized plants if they run only on solar energy. So this comparison illustrates the sheer scale of deployment needed to meet the National Green Hydrogen Mission target. And India will require a solar footprint the size of a major city and thousands of Gale-scale electrolyzer plants, representing one of the largest green hydrogen infrastructures anywhere in the world. So now that we've understood why hydrogen and collaboration are essential, let's take a step back and look at India's hydrogen value chain. from how hydrogen is produced to how it is stored and distributed, and then finally used. So in India, hydrogen production is shifting from gray to green hydrogen, and the National Green Hydrogen Mission envisions scaling up green hydrogen through electrolysis powered by renewables. So companies like NTPC, Reliance, Adani, and Greenco are investing in large-scale electrolysis projects, particularly alkaline and polymer electrolyte membrane systems. We're also exploring biomass gasification and photoelectrochemical splitting, which are still in early research stage. And the next big focus area is indigenization of electrolyzer technology. And that's where academic and industrial R&D partnerships are crucial at the moment. Next, we have storage and distribution. So once the hydrogen is produced, storage and transport become key challenges. And currently, India relies primarily on compressed gas cylinders at high pressure. But for long-term scalability, liquid hydrogen and chemical carriers such as ammonia and methanol are being explored. And then Indian Oil, NTPC, and HPCL are already setting up hydrogen refueling stations and blending pilots in city gas grids. And a long-term vision includes a dedicated hydrogen pipeline network, much like our existing natural gas infrastructures. And then hydrogen has multiple end-use pathways in India. In transport, hydrogen fuel cell buses and trucks are being tested by NTPC and Ashok Leyland. In industry, refineries, steel, and fertilizer plants are preparing to replace grey hydrogen with green. And power generation is emerging as a key use case, blending hydrogen with natural gas for turbines or using it in fuel cell based microgrids for remote areas is also an option. And finally, exports. So, India is positioning itself as the global supplier of green ammonia and hydrogen to countries such as Japan, Korea, and Europe. So, as we can see, hydrogen forms an entire value chain, and every link in that chain, from research to deployment, offers massive scope for innovation. Now, next we look at where academia fits into this ecosystem, the knowledge and research engine driving India's hydrogen revolution. So now we look at the role of academia because universities and research institutions are truly the backbone of India's hydrogen innovation ecosystem. Most of the breakthroughs in materials, electrolyzer performance, fuel cell design, and hydrogen safety originate from academic labs. So the first and most important contribution is fundamental R&D, and institutes like IIT Delhi, IISc Bangalore, and BHAL R&D are driving cutting edge research in catalysts, membranes, bipolar plates, and next generation electrolyzer and fuel cell materials. This early stage scientific work is critical because the performance and cost of green hydrogen technologies depend heavily on material breakthroughs. Then, second, we have academia providing test infrastructure and centers of excellence that are essential for validation of current technology. Facilities such as CSIR, CERSI, IIT Madras, HTIC, and the test beds at IIT Bombay offer advanced characterization tools, fuel cells and electrolyzer testing rigs, and reliability evaluation platforms. These are the places where prototypes are tested, performance is measured, and industry technologies are verified. And third, academic institutions play a major role in skill development. So we have IITs, IIScs, NPTEL, and other institutes now offer hydrogen technology courses, modeling workshops, simulation training, and even hands-on demonstration kits. This is crucial for building the workforce that India needs: engineers, researchers, technicians, and faculty trained specifically in hydrogen. And finally, academia acts as a launchpad for innovation. Programs under DST, MNRE, and SERB support university-based startups, research consortia, and deep tech innovation in hydrogen production, storage, safety, and mobility. Many of India's hydrogen startups today were incubated within IITs and NITs, benefiting from mentorship, lab infrastructure, and early investment. So, academia is not just about contributing to hydrogen research, it is enabling the entire ecosystem from fundamental science and talent development to testing, incubation, and industry partnerships. So, one of the most important roles of academia in the hydrogen ecosystem is conducting deep fundamental research, the kind of science that directly determines the cost, efficiency, and scalability of hydrogen technologies. So, a major reason hydrogen stacks are expensive today is the use of the rare and costly elements in membranes and catalysts, materials like platinum, iridium, and rhodium. Academic research in materials science is essential for developing alternate catalysts, lower loading membranes, and novel coatings. And these innovations can dramatically reduce the capital cost of fuel cells and electrolyzers. Next, we have process innovation. So, academia also drives process level innovations, simplifying chemical synthesis routes, improving reaction workflows, and reducing the number of processing steps. Better process engineering leads directly to higher manufacturability, greater consistency, and lower production costs. And today, electrolysis is still an inefficient process, and nearly 60% of the input energy is lost across electrolysis, water purification, compression, drying, and storage. So, academic research is crucial to improve water treatment efficiency, membrane hydration control, compression and storage technologies, and overall system integration efficiency. So, incremental improvements in each of these areas collectively result in a much higher hydrogen yield and significantly lower operational costs. So, next we have some emerging research scope where exciting one exciting area of research is direct seawater electrolysis, which has gained significant attention due to India's massive projected water demand for hydrogen production. So, why do we need direct seawater electrolysis? So, by 2030, as um, we discussed before, we need to produce 45 million cubic meters of demineralized water to meet the green hydrogen targets. And producing and transporting this purified water leads to energy losses, higher operational costs, and pressure on freshwater resources. So, this is why researchers are exploring ways to use seawater directly as feedstock without passing it through conventional reverse osmosis or desalination steps. So, there are two different technology pathways that are being explored right now. The first pathway being inhibitor enhanced alkaline slash AEM electrolysis, where the first pathway is chlorine is being explored is adding a chlorine evolution inhibitor into existing alkaline or AEM electrolyzer systems, and this prevents the formation of chlorine gas at the anode, which is the biggest challenge in seawater electrolysis. So this advantage is that existing electrolyzers can be retrofitted with minimal modification and no desalination would be needed, which means no additional energy penalty, making the process more cost effective. And then we have technology pathway 2, which is direct coupling directly coupling the electrolyzer with a forward osmosis module. Here, the forward osmosis module pulls water across naturally using osmotic pressure, removing salts and impurities right before the electrolysis step. This reduces scaling, corrosion, and membrane degradation while still avoiding the high energy consumption of large-scale desalination plants. And if both of these pathways show enormous promise, and if successful, both seawater electrolysis could eliminate one of the biggest bottlenecks in green hydrogen production, which is freshwater demand, and make coastal hydrogen hubs for far more sustainable and cost competitive. Another emerging technology is solar water splitting. So this is one of the most exciting emerging pathways for low-cost green hydrogen. And today, most green hydrogen relies on a two-step process. A photovoltaic panel generates electricity, and that electricity then powers an electrolyzer. While effective, this architecture brings two challenges: high capital cost and energy losses during electrical conversion and transmission. So researchers are exploring whether we can combine both steps into one device. That's where uh, solar water splitting or PEC hydrogen production aims to do. Instead of using photovoltaic plus an electrolyzer, we use specially engineered semiconductor photoelectrodes that directly absorb sunlight and split water. So this integrated approach offers several advantages, such as a simplified system, fewer conversion losses, and the possibility of significantly lower cost green hydrogen production. It also fits perfectly with India's strengths, which is abundant sunlight and a need for decentralized hydrogen production. This image on the right shows a typical multi-layer photoelectrochemical structure where tin oxide, silicon, and NiO2, each layer performing a different function. When sunlight hits this stack, electrons and holes are generated, and electrons move towards the hydrogen evolution site, while holes drive oxygen evolution. In other words, the device converts sunlight directly into hydrogen without needing an external power supply. Although still in research stages, photoelectrochemical water splitting is a promising direction for next generation hydrogen technologies. Another key emerging research area is the development of advanced hydrogen carrier fluids, especially as India looks to scale exports and long distance hydrogen transport. Today, ammonia is the most widely used hydrogen carrier because it is energy dense and easy to transport internationally. However, ammonia is also highly toxic, corrosive, and difficult to handle, which makes large-scale logistics and safety management extremely challenging. So, a promising direction is the conversion of hydrogen into reversible organic carrier fluids, often known as LOHCs, liquid organic hydrogen carriers. These are stable organic liquids that chemically bind hydrogen and release it on demand. So the major advantage is that these carrier fluids can be transported and stored just like conventional fuels using existing pipelines, tankers, and fuel infrastructure. And this makes hydrogen logistics simpler, safer, and far more cost effective. And for India, this could significantly boost hydrogen exports, and for industries operating in remote regions, LOHCs could serve as efficient captive hydrogen solutions without the need for high pressure storage or cryogenic systems, which require a lot of energy. And then overall, organic hydrogen carrier fluids represent a major opportunity, improving safety, reducing handling costs, and enabling true large scale hydrogen mobility and trade. And then let's look at a very promising solid state hydrogen storage method, which is metal hydrides. So, metal hydrides store hydrogen by chemically absorbing it into the lattice of a metal or alloy. When hydrogen gas comes in contact with certain metals, it gets reversibly absorbed, forming a metal hydride compound. And to release the hydrogen, you simply add controlled heat, and the hydride decomposes back into the metal and the hydrogen gas. We're essentially storing hydrogen in solid form, which makes it much safer and much more compact than pressurized gas tanks. So let's talk about the materials that are used. So alloys like lanthanum nickel 5 and titanium iron alloy are already used commercially, and they absorb hydrogen at low pressure around 1 to 10 bar and are quite stable, though they store only about 1 to 2 weight% of hydrogen. And on the higher capacity end, we have materials like magnesium hydride and sodium alunate, which can store up to 7.6 weight%, but they require temperatures of about 250 to 300 degrees Celsius to release the hydrogen. Researchers are also exploring complex hydrides like borohydrides and alanates, which have even greater capacity, but they're still in early R&D. If we compare metal hydrides with high pressure gas storage, volumetrically they are far superior since they can store up to 120 kilograms of hydrogen per cubic meter, which is nearly three times what a 700 bar tank can store. But gravimetrically, they fall short, and these systems are very heavy, and the hydrogen to total mass ratio is low since the tank is metal and we have a lot of metal powder inside the tank, as you can see in the image on the right. But they're also very safe, operating at low pressures with hydrogen chemically bound in the solid matrix. So the main challenges are weight, cost, and thermal management because these materials are heavy and they need heating and cooling to function efficiently. They're best suited for stationary applications like backup power systems or renewable energy integration, where space and weight are less of a constraint. Some specialized mobile use cases are submarines, military drones, or off-grid hydrogen vehicles that have already tested hydride tanks, but widespread vehicle adoption still faces hurdles. So, in summary, metal hydrides offer excellent safety and high volumetric density, but improvements in weight and thermal efficiency are key to unlocking broader applications.
Thank you, Ekaansh. I would love to carry on with the remainder of this presentation. So I understand we are a bit short on time, so I will try to wrap this up as soon as possible without omitting a lot of information. Starting with the role of academia with testing infrastructure. So in September of this year, Ekaansh and I actually visited the first R&D conference in Delhi, specifically dedicated to the hydrogen economy of India. And what came up repeatedly was a lack of testing infrastructure in India and the primary bottleneck for developing new kinds of technologies. And because, as we know, to test field viability or to go from TRL 3 and 4 all the way to TRL 6, 7, or to commercial readiness, we need testing infrastructure. So talking a little bit about what testing infrastructure in the hydrogen economy entails, starting with performance testing, both for electrolyzers and fuel cells. This involves measuring hydrogen output per kilowatt hour, including the stack efficiency, polarization curves, IV characteristics, and degradation behavior. Most commercial electrolyzers operate at 55 to 65% efficiencies. And evaluating improvements requires precise sensors, water purification systems, and pressure regulation. Then comes durability testing. This is critical because degradation directly affects the cost of an electrolyzer stack. Um, this is mainly caused by hydrogen embrittlement or due to because hydrogen needs to be very pure. There are certain particles in hydrogen that can degrade electrodes and the membranes of an electrolyzer, which is why long duration cycling tests of over 1000 plus hours is industry norm when it comes to identifying failure modes. So such tests are essential for R&D grants and getting that industrial validation. Then we come to adaptability of variable renewable energy. So India's hydrogen will predominantly be renewable energy based, which is the goal. That means electrolyzers must be compatible with fluctuating solar and wind input. And in order to test this, we require programmable power solutions. So simulating different kinds of loads and advanced controllers, institutions need to be capable of running such natural simulations and identify the natural loading and the natural real world scenarios. And finally, we have purity testing. So fuel cell grade hydrogen must meet specific ISO standards. ISO standards such as 14687. This will require specialized again systems and testing infrastructure such as gas chromatography, impurity detectors, and sensors to detect moisture, oxygen, and all the variables associated with system efficiency. Can we go on the next slide? Okay. So now talking about how central and government labs and even other private research institutes such as IIT um, set up test facilities, and how do you actually get funding for such testing facilities. So facilities can be a great way for a university to actually um, be actively involved in R&D with green hydrogen. So in terms of collaborating with new startups, industry players, and having that testing infrastructure will really help them sort of be a part of the development process, and also in that way build expertise for future developments and future projects. So it is a win-win situation. So here we are prepared based on the National Green Hydrogen Mission. Certain guidelines were given on uh, do what does a funding proposal look like when applying to build a test facility. Starting with the technical scope, you need to have facility maps of the green hydrogen value chain. So clear list of tests, what kind of equipment is required, and what kind of tests would be carried out, all following international standards. So much of these standards can be found online with a little bit of research. And what can be done is to loop in other international universities where the hydrogen R&D value chain is strong, such as Germany or Korea. Safety is another very important factor. So a safety management plan needs to be a part of the proposal. And moving on to the execution plan, uh, detailed capex and installation plan within 12 to 18 months timeline is required. So what would be an estimated capital expenditure that the university is looking at? Again, implementation responsibility assigned to an executing agency needs to be assigned. All regulatory approvals need to be identified. Environment, again, emphasis on safety is required. How would those test systems would be commissioned? Okay, would the vendor themselves would be coming in? Would they be training the faculty to install the test machines? Everything needs to be a part of the funding proposal. Next, we have accessing model and financials. Each testing facility needs to be open for use to industry professionals and academia both. So if there is another university that would like to basically use the testing facilities that you are planning to set up, uh, they should be allowed to do so, and that is a key factor in availing funding for such campuses. The the operational expenditure of your requirement cannot uh, exceed 15% of the total grant that is given by the government. That is planned to be given by the government in a span of over 4 years. In case of co-funding, so let's say there is another university that wants to go in that NIT would like to collaborate with or co-fund a research facility with, that model needs to be clearly defined. Finally, we have outcome and deliverables. So what kind of, again, parameters would be tested and how would data be collected? What is the quality control of the data? How the robustness of the data be tested? So those sort of details need to be part of a test facility funding proposal in the hydrogen economy. Next slide. Now we talk about skill development and knowledge. So one of the fundamental roles of an academic institution is to uh, develop skills within the faculty and also the student body, that to uh, state of the state of the art with state of the art you know, talent and skill development. So what we normally
Sir,
say
your voice is breaking, sir.
okay. Now Yeah, am I audible now?
Yeah, yes, sir. Please proceed.
Yes.
Yeah,
Okay.
please proceed.
Awesome. Great. I'll just wait for Ekaansh to screen share. Okay, great. Yes. So as I was saying, importance to simulation softwares. There are a lot of simulation softwares available in the market. What simulation softwares allow us to do is this rapid iteration of designs and to not get 100% representations of how it will perform in the real world, but you can test different materials, different designs, and the effect of variables such as heat and physical sort of forces and stresses on every design before you can actually get it fabricated or prototyped in the real world. This significantly cuts costs and the risk by reducing repeated physical testing. We can go to the next slide. Okay. So here is a quick summary of the industry simulation softwares that are available and have been used to make developments in the hydrogen value chain. So, for instance, we have the Aspen HYSYS, where a university in Brunei used Aspen HYSYS to simulate hydrogen production from plastic waste. So, this was a techno-economic assessment. Then we have a university in South Korea, which is a leader in hydrogen development and R&D using COMSOL multiphysics, a 3D modeling software that helps them model the water electrolysis in a PEM based cell. This included the flow simulation and also the electrochemistry, so where you can vary parameters such as the voltage, the current, the power. Then ANSYS being one of the most popular softwares globally for end-to-end simulation requirements. So you have China using fluent-based CFD study on hydrogen leakage and explosion behavior in fuel cell buses. So hydrogen leakage and explosion is something that is even dangerous to test in the real world. So this is where you see how the power of simulation softwares can really help a university or even um, a student that learns how to use a simulation software can be great contributors to the industry once they pass out and go into the real world and find a job in the hydrogen sector. Then we also have a a software by Siemens. A lot of emerging universities and even companies in India are beginning to use the Siemens SimScape software, helping them model their hydrogen electrolyzer operations and to even test the robustness of their system under different conditions. Next slide. Now we can talk a little bit about hands-on training and the hands-on skill development. So handling hydrogen is something that a lot of universities are not exposed to, the student body or even the faculty. So in-house hydrogen skill development or the creation of hydrogen labs is something that the government is really pushing for at the moment. They would like students to understand how hydrogen is made from electrolyzers and how fuel cells can use hydrogen to create electricity. How this can there is understanding of instrumentation. There is the know-how of using gas flow controllers or sensors, and what kind of tests do industry players run in this sector when dealing with their own hydrogen electrolyzers and fuel cells. So there are such hydrogen educational and lab kits that can be installed at universities to run lab demonstrations and lab experiment programs with students, with faculty, and it sort of just complements the entire R&D workflow. Also gives students a stronger placement opportunity at emerging local hydrogen economies. You can also run capstones and build capstone projects around lab setups and test hydrogen, the robustness of any system that is being designed or tested. Okay, next slide. Now, the next and final step that we have in the role of academia is startup incubation. As Ekaansh also initially mentioned during at the beginning of this presentation, that the government is really looking forward to new hydrogen related startups to come up and deploy, at least at right now at the pilot scale, deploy their solutions in the market. So there are certain ways that universities are going about this process. So for example, IIT Delhi has been running the Foundation for Innovation and Technology Transfer, which is the FITT. So what they have achieved to do is they have developed a technology transfer ecosystem where and an incubation program that is a closed loop system in itself. So there is the flow of this of such a program follows a 6 to 7 step process where a PhD or a postdoc researcher first develops a breakthrough technology. That technology is demonstrated at the lab scale, which is your TRL 3 to 4. After that, we have a research team forming a startup company, or an existing industry partner comes in and collaborates with the research team to incubate a startup within the university. So this sort of turns your researcher into a CTO, Chief Technology Officer of the newly formed startup. And this is a very strong prevailing culture in a lot of R&D institutes. After that, a equity model is created where the university, the research team, the partnering industry player all benefit from an equity model. They get lab access, seed funding from the government, from the university itself, and that sort of any revenue generated from that is fed back to the university. So it creates this win-win situation for all parties involved. Another such initiative is the ATAL Incubation Center, a flagship initiative, and it is an umbrella structure that has been mandated to promote innovation and revolutionize the entrepreneurial ecosystem in the country. So they give a grant of up to 10 rupees, 10 crores for a maximum period of 5 years for setup and infrastructure. IIT Raipur is a member institute of the ATAL Innovation Mission. Okay, next slide. So this is a brief map and a process flow diagram of sorts of how academia and industry collaboration works. We have the apex policy and funding layer, then the central research organizations such as the CSIR. The map on the right is a map of all the CSIR central research institutes working on different domains in India. Then we have the academic and R&D institutes, we are IITs and NITs, and then we have the technology transfer offices. So now what is happening is these technology transfer offices, a lot of times are now being integrated with the academic institutions itself, so that there is a better commercialization process of any technology that is, or any breakthrough that is created in a university. A lot of times good breakthroughs are take very long time to become commercialized. So this is a emerging trend and should be really considered as a part to efficient commercialization of green hydrogen technologies. Next slide. Now, again, this is another representation of in a very specific green hydrogen context of how the institutions or the country's resources flow when it comes to green hydrogen R&D. So the Ministry of Renewable Energy leads the green hydrogen mission, and they operate their schemes such as the R&D scheme or the startup pilot scheme, project schemes. So that is your tier one layer of the resource framework. Then we have the tier two resource framework, which is the centrally funded research labs. So these are all your CSIR institutes with very specific domain expertise. What is good about these facilities is that they have a pre-existing access to government funding, and they tend to create these centers of excellence in the hydrogen space. There are still not many of them that have hydrogen infrastructure or hydrogen research infrastructure, but how they are positioned in a way to collaborate with other research institutes, and they actually invite other research institutes to utilize their facilities, um, so that uh, development and breakthroughs can be fast tracked in the country. And then there is the tier three sort of resource framework, which is one of the most important, which is NITs and the IITs, that as innovation engines, academic institutes, they function as both knowledge generators and also commercialization enablers. They are the ones directly talking to the local industry, and they enable a structured dual track approach, where track one is fundamental and applied research, but they also are the ones who carry out the field tests and the prototyping, and basically getting that final proof of concept before full scale commercialization. Next slide. So now, how do you deploy a breakthrough in industry? Okay, let's say, I think even our previous speaker mentioned that a lot of times breakthroughs in the lab are not deployed in the industries successfully. And this slide sort of stresses on why industry deployment or partnering or collaborating with industry is so important. So the first path to do so is direct industry sponsored research. So an example of that is a company, Omium International, which is a foreign company, collaborated with a CSIR institute for developing advanced materials in PEM electrolysis. So they directly fund this research at our research institutes and address very specific technical challenges. And the next thing we have is consortium-based R&D. So this is where the SHIP Strategic Hydrogen Innovation Partnership sort of sits. Here, government institutes and central labs, plus our research institutes such as an NIT Raipur and an industry partner, all three come together to form a consortium and collaborate on multi-year projects. So this really brings that scale of deployment, and ensures a smooth flow of funds, and national level infrastructure is leveraged, because you have all three parties: the policymaker, the innovator, and the executing commercialization partner. being a part of this of a consortium. The third one is a joint development agreement. So similar to consortium based, but again more focused on MNC, or in this case, multiple universities and research institutions come together to co-develop technologies instead of uh, the research partner or a industry partner coming and giving them a project or a project sort of goal. So an example of this is how L&T and IIT Bombay collaborated to scale up commercialization and manufacturing of their electrolyzers, alkaline electrolyzers. Next slide. So now let's talk a little bit about how NIT Raipur can be a strong force in the hydrogen R&D ecosystem. So on the right, you have images of Adani, the Adani organization launching India's first hydrogen-powered mining truck in Chhattisgarh. Mining, steel, and even biohydrogen. So mining and steel directly being benefiting from the hydrogen sector would be mining. In terms of mining, all heavy duty trucks, your construction machinery, your loaders, your excavators, a lot of development happening on retrofitting their engines with hydrogen ignition or hydrogen ICE engines, hydrogen combustion engines. And because of the high energy density in hydrogen, this is increasing in viability. JCB, a prominent construction equipment company, is already working on their hydrogen combustion engine. So in the mining sector, this is very valuable. Then comes steel, direct reduction of steel of coke, and to make steel using hydrogen is going to be super valuable. JSW has already commissioned a plant to start using hydrogen to directly reduce iron ore and produce steel out of it using green hydrogen. So there is a massive decarbonization opportunity over there. Again, a lot of universities tend to collaborate with MNCs or the big sort of pan-India companies. In Raipur and Chhattisgarh, there is a good opportunity to collaborate with local industries, the local steel industry, the local farming industry, to basically develop breakthroughs in biohydrogen, bioethanol, and for using hydrogen as a feedstock to decarbonize hard to abate sectors. So this will sort of really, push the limits of regional decarbonization. You have the big companies already, with working on this on their big plants, but regional play is going to be equally important. And deploying solutions in regional clusters, regional industrial clusters, is where strong value is projected. Next slide. So another slide to reinforce optimization of IP management, incubation, and licensing. So as I previously mentioned, incubating startups, using the breakthroughs that are developed in-house within the universities will be super valuable. But to achieve that and to do it right, to achieve that well, you need to manage IP and technology transfer pipelines well. So you revising KPIs, key performance indicators, to give credit to the researchers, to the research team, to give them to coming up with the right equity models for research teams and the university. And these clauses need to be a part of PhD thesis so that in case of research breakthroughs, they can be commercialized well in good faith, and it can create an ecosystem of innovation within the university. So licensing, technology transfers are very important, and because the industry is so emerging, um, there is there is a lot of opportunity to do pilots, to do pilot testing, to basically demonstrate technologies. So it is important to protect the IP and also to optimize its management. Next slide. Again, it is important to leverage collaboration and funding architecture. So the Green Hydrogen Technology Accelerator platform called GHTAP is a membership that is underutilized. It is a platform that provides access to different existing testing facilities, gets you access to industry mentorship and funding connections specifically for hydrogen R&D. So NIT should really look into institutionally joining um, pre-existing hydrogen clusters. We now have hydrogen valleys or hydrogen hubs at Deen Dayal Port in Gujarat. There is one coming up in Pune. There is one coming up in the southern part of India. So um, the Cochin shipyard is also going to be a green hydrogen hub. So leveraging these hydrogen clusters and ecosystems would be a strong strategic opportunity. Next slide. Okay. So just to wrap things up, this was all that we wanted to talk to NIT Raipur about in terms of the importance of R&D, the R&D ecosystem, and the importance of breakthroughs in hydrogen. There is a lot of work to be done, a lot of efficiency gains that can be achieved in systems. But for that, skill development and education remains the primary backbone. So something that Hydrogen Network India does is training workforces in hydrogen, developing industrial SOPs and fire response, providing lab kits for skill developments, and building those lab infrastructures. Also giving simulation software training and developing the overall skill set both for students and faculty members across India. And finally, next slide. So finally, we have a webinar in December that will focus on waste to hydrogen pathways for a green future. So we have a renowned speaker and a renowned expert who's also the founder of Revive Clean Tech, Mr. Sanjay Singh. He is from IIT Indore, and he will be talking about waste to hydrogen pathways for a green future. So I will leave this slide on here for anyone interested, and feel free to ask us any questions. That is the end of our presentation. Thank you so much.
Yes, participants, do you have any questions? Yeah, I think there is no questions, but
Awesome.
the topic is very much interested, sir. Yeah, given. So mostly, what is the academic requirements and how we can develop this hydrogen technology? to the academic and academic research and the collaborative, how the collaboration to the industry, especially for hydrogen R&D. So any questions from the participants?
Sir, good evening, sir.
Yeah, please.
Sir, in this in point of storage of hydrogen, in case of what type of polymer composites can we use? Either synthetic or natural. What type of polymer composites uh, we can uh, we can use for this storage of hydrogen? Can you please explain, sir?
So right now there are for gas-based hydrogen storage, there is type 3 and type 4 cylinders. So normally hydrogen gas storage or any industrial gas storage traditionally was stored in heavy mild steel and steel sort of uh, canisters or cylinders, you may say. And now we have emerging technologies to use carbon fiber and glass fiber to with aluminum liners. So you have aluminum liners and a weave of glass fiber strands with epoxy coating are done around these cylinders. And what uh, has been achieved is a high pressure capacity for that the cylinders can withstand while being just 25 to 30% of the weight. So a glass fiber based composite cylinder would be called type 3, and the most advanced one is now emerging in India called type 4 cylinder for storing hydrogen as a gas. So type 4 cylinder uses carbon fiber as a to basically take an aluminum or any other metal alloy as a liner, and then you have weaving the weaving process that is done around this liner with this material that is coated in epoxy to build a high pressure vessel.
Okay, sir. Thank you, sir. Sir, means can we use fiber filaments or fiber fabrics for the Type 4 tanks? And
So for
HDP also, I think we can use it.
I'm not sure about
HDP.
HDP, but for carbon fiber, uh, there are machines that use filaments. In case of specifically in the case of type 4 cylinders, what they do is they use pre-preg fibers to and an automated arm to basically line a cylinder that is rotating on a fixed axis. So what I'll do is I'll just show you a quick video on that or share the link.
Okay. Yes. Thank you very much, sir. Thanks.
Yes, I'll just put that in the chat.
I think right now
It is
mostly they are using the synthetic polymer composites only. The natural fiber composites are not yet tested so far, and a lot of research work is going on in polymer composites, as per my knowledge. Still, these composites use for hydrogen storage is in inception stage. A lot of research work is going on. I
correct.
think people can take up the topics because I am also working in this area for hydrogen storage tanks for aerospace industrial applications. So, so a lot of work is there to be done.
Absolutely.
Yeah. So I think there is no any other questions from the other participants. Yeah. If not any questions, I want to conclude the sessions. On behalf of the organizing committee, the Department of Mechanical Engineering and Metallurgical Material Engineering, NIT Raipur, and all the participants of this ATAL FDP, I extend our heartful gratitude, our esteemed speakers, Mr. Dhrumil and Mr. Ekaansh, for the delivering an insightful and inspiring expert talk, especially on the role of academic and industry in hydrogen R&D. Sir, your deep expertise and the clear articulations of the emerging opportunities in hydrogen research have truly enriched our understanding. The way you highlighted the collaborative pathways between academia and industry has opened new directions of our research, faculty, and students. You are also emphasized that what is the opportunities for the NIT Raipur. It is not only NIT Raipur, you have given the example to the NIT Raipur that it may be similar to the any other academic institutions. We sincerely appreciate the time and effort you devoted on this session, and we are gratefully for the acknowledge you have shared with us today. I also extended my thanks to all the participants, faculty members, and organizers for their active engagement and support in making this session a grand success. Once again, thank you, sir, Mr. Dhrumil and Mr. Ekaansh, for your valuable
Thank you, Dr.
contribution to
Swami.
this FDP.
Thank you, Dr. Swami. Thank you, Dr. Bhargavi, for inviting us to present in front of all the esteemed members of this meeting. Thank you so much.
Yeah, thank you, sir.